Hello, and welcome to Space for Sleep. Voyager is the story of two small machines that went farther than their builders could ever follow. They were launched in 1977, 16 days apart, from Cape Canaveral. They were built with the technology of another era, before smartphones, before the public internet, before modern personal computing, before most of the spacecraft engineers working today had even chosen their careers. Each spacecraft carried cameras, magnetometers, plasma and particle instruments, ultraviolet and infrared spectrometers, radio systems, and cosmic ray detectors. Each carried a high-gain antenna just 3.7 meters wide. Each carried a power source warmed by the slow radioactive decay of plutonium. Each carried computers with less memory than a small modern image file. And still, nearly half a century later, they are not only remembered, they are still mission assets. Voyager 1 is now more than 25 billion kilometers from Earth, the farthest human-made object ever built. Voyager 2 is more than 21 billion kilometers away. Both have crossed the heliopause, the boundary where the sun's outward flow of solar wind gives way to the local interstellar medium. They are not outside the sun's gravity. They are not beyond the Oort cloud. They are not near another star. But they are outside the heliosphere, outside the protective bubble of particles and magnetic fields blown by the sun, and that makes them the only spacecraft ever to directly measure interstellar space. Their radio signals are unimaginably faint by the time they reach Earth. A command sent to Voyager 1 now takes more than 23 hours to arrive, and the answer takes more than 23 hours to return. A full question and answer with the most distant spacecraft in history takes nearly 2 days. Nothing about the mission is real-time anymore. Every command is sent into silence. Every response, if it comes, is already a message from yesterday. This is what makes Voyager more than a spacecraft story. It is a story about engineering patience. It is a story about orbital timing. It is a story about the outer planets before close-up exploration and after it. It is a story about two machines that revealed volcanoes on Io, an ocean world at Europa, ring structure at Saturn, the strange tilted magnetism of Uranus and Neptune, nitrogen geysers on Triton, and the shape of the sun's invisible boundary with interstellar space. It is also a story about human beings deciding to attach a record of Earth to a spacecraft that would almost certainly never be found, simply because the act of doing so said something about who we wanted to be. The original Voyager mission was not designed to last 50 years. The approved primary mission was the exploration of Jupiter and Saturn. The larger dream, the grand tour, reached further: Jupiter, Saturn, Uranus, Neptune, and possibly beyond. Budget and schedule reduced that dream, but the planetary alignment remained, and Voyager 2 carried the dream forward after Voyager 1's Titan flyby sent it away from the remaining planets. What began as a 4-year planetary mission became the only completed close-up tour of all 4 giant planets. Now the mission has entered its final living chapter. Instruments have been switched off to save power. Heaters have been sacrificed. Engineers have rewritten old code around failed memory, revived long-dormant thrusters, and made decisions measured in watts. In 2026, NASA shut down Voyager 1's low-energy charged particles instrument to keep the spacecraft alive, leaving its magnetometer and plasma wave subsystems still operating. Voyager 2, closer but also aging, continues with its own reduced set of instruments. The end is coming, but not as a single dramatic failure. It is coming one at a time. That slow ending gives the story its shape. Voyager is not only about distance. It is about endurance. It is about what can still be learned when almost everything has already been used up. It is about a signal from the dark, still reaching Earth from a place no other machine has ever sampled. Every year that the mission continues now feels borrowed. That borrowed time is scientifically valuable, but it is also narratively powerful. Voyager has passed the point where endurance feels normal. Each signal is no longer simply an update. It is a reminder that something built in 1977 is still participating in the present. A machine does not know that it is old. It does not know that it is famous. It does not know that people on Earth feel tenderness toward it. It follows commands, measures fields and waves, maintains its orientation, and transmits. The meaning belongs to us. But that is true of all exploration. We send instruments outward, and then we interpret not only what they find, but what their journey says about us. So we begin with the alignment that made the journey possible, and with the decision to send 2 spacecraft through a doorway in time that would not open again for roughly 175 years. A useful way to feel the Voyager mission is to hold its timeline without rushing through it. The launches happened in 1977. Jupiter came in 1979. Saturn came in 1980 and 1981. Uranus came in 1986. Neptune came in 1989. The pale blue dot came in 1990. Voyager 1 crossed the termination shock in 2004, crossed the heliopause in 2012, and entered interstellar space. Voyager 2 crossed the heliopause in 2018. The spacecraft were already old by ordinary engineering standards when many of their most symbolically powerful moments happened. This means the Voyager mission is not a single event. It is a lifetime. It belongs to several eras at once. It began during the Cold War, before the first space shuttle flight, before the first confirmed exoplanet around a sun-like star, before Hubble, before Galileo at Jupiter, before Cassini at Saturn, before New Horizons at Pluto, before Webb. It continued through all of those eras and outlived many of the missions that came after it. That continuity gives Voyager a different emotional texture from a dramatic launch or landing. A launch is a moment. A landing is a moment. Voyager is duration. It is the accumulated meaning of decades of small updates, long waits, fading power, distant signals, and repeated decisions not to give up while anything useful. The third lesson is that exploration does not end when the headline ends. The public remembers Jupiter, Saturn, Uranus, Neptune, the pale blue dot, and the golden record. But the mission's continued value comes from long, quiet work, tracking, calibrating, commanding, analyzing, maintaining, deciding which instrument to preserve for one more year. Great missions are not only made by moments, they are made by maintenance. The fourth lesson is humility. Almost every world Voyager visited was stranger than expected. That is a useful thing to remember whenever we imagine that remote observations have already told us what a place will be like. The universe often looks simpler from a distance than it becomes up close. The concept of the Grand Tour, a spacecraft mission that could use the orbital mechanics of the outer solar system to visit Jupiter, Saturn, Uranus, and Neptune in sequence, was discovered not by a senior scientist at NASA, but by a 25-year-old graduate student named Gary Flandreau, working at the Jet Propulsion Laboratory in Pasadena during the summer of 1965. Flandreau was tasked with identifying future mission opportunities in the outer solar system and had access to a computer powerful enough to calculate the orbital trajectories of multiple planets simultaneously over extended time periods. What he found, examining the planetary positions projected forward into the 1970s and 1980s, was that Jupiter, Saturn, Uranus, and Neptune would be arranged in a particularly favorable configuration in the late 1970s, a configuration that recurs only roughly once every 175 years. In this configuration, the gravitational field of each outer planet, encountered in sequence, could be used to accelerate the spacecraft and redirect its trajectory toward the next planet, a technique called gravitational assist or slingshot. Gravitational assists are not a new idea in principle. The mathematics of how a spacecraft could use a planet's gravity to gain velocity had been understood for decades, But Flandreau's calculation was the first to demonstrate that a single spacecraft, launched at the right time with the right trajectory, could use this technique 4 times in succession to tour the entire outer solar system in roughly 12 years, visiting all 4 giant planets in a single mission that would otherwise require multiple spacecraft and several decades. The discovery sparked immediate interest at JPL and NASA, and the Grand Tour concept became an official NASA study. The initial plan was ambitious: multiple spacecraft, multiple launch dates, visiting all 4 outer planets, and potentially Pluto as well. Budget constraints through the late 1960s and early 1970s progressively reduced the scope until what survived was a mission called the Voyager program. 2 spacecraft, a primary mission to Jupiter and Saturn, with the possibility of extended missions to Uranus and Neptune if the spacecraft survived that long and funding was available. The planetary alignment that made the Grand Tour possible, the alignment Flandreau identified in 1965, would be available only for a specific launch window in the late summer of 1977. Voyager 2 launched on August 20th, 1977, 2 weeks before Voyager 1, which followed on September 5th. The numbering 2 before 1 reflects the fact that despite launching first, Voyager 2 would take a longer, slower trajectory and arrive at Jupiter after Voyager 1, which took a faster path. The gravity assist is one of the most elegant tricks in spaceflight because it looks, at first, almost like getting something for free. A spacecraft approaches a planet from behind or from the side, falls into the planet's gravitational field, swings around it, and leaves on a new trajectory. From the spacecraft's point of view, relative to the planet, the speed going in and the speed coming out can be almost the same. But the planet itself is moving around the sun. In the sun's frame of reference, the spacecraft can steal a tiny amount of the planet's orbital energy, leaving faster than it arrived. The planet slows by an immeasurably tiny amount, far too small to matter, and the spacecraft gains enough speed and direction change to reach the next world. This is how Voyager became possible. Chemical rockets alone could not send a spacecraft directly to Uranus and Neptune on a practical schedule with 1970s launch vehicles. But Jupiter and Saturn could act as moving gravitational handles. Each encounter could bend the path and change the energy. The planets were not only destinations, they were engines. The timing had to be precise. Launch too early or too late, and the next planet would not be in the right place when the spacecraft arrived. Aim too high or too low through the gravity well, and the spacecraft would miss the next target by millions of kilometers. The entire mission was a long chain of consequences, where a trajectory decision at Jupiter shaped the path to Saturn, and the Saturn encounter determined whether a spacecraft could continue to Uranus and Neptune. Voyager 1's path was chosen to give priority to Titan. Titan was scientifically irresistible, a moon larger than Mercury, wrapped in a thick atmosphere. That close Titan flyby bent Voyager 1's trajectory out of the plane of the planets, ending its chance of continuing the Grand Tour. Voyager 2 took the longer road. It preserved the geometry needed for Uranus and Neptune, and because of that, it remains the only spacecraft ever to have visited either ice giant. This trade-off is one of the reasons the 2 spacecraft design was so powerful. Voyager 1 could take the scientifically valuable Titan path. Voyager 2 could preserve the outer planet path. Together, the 2 missions did what one spacecraft could not have done without sacrificing something essential. The launch order itself is a small reminder that missions are human systems as much as mechanical ones. Voyager 2 launched first because its trajectory required the earlier departure. It rose from Earth on August 20th, 1977, aboard a Titan III Centaur rocket, beginning the long route that would eventually carry it past all 4 giant planets. Voyager 1 launched later, on September 5th, but on a faster trajectory. It overtook Voyager 2 before the Jupiter encounter and reached the giant planet first. The numbering therefore describes arrival sequence, not launch sequence. There is something pleasingly untidy about that detail. The most distant human object is called Voyager 1, but it was not the first Voyager to leave Earth. The only spacecraft to visit Uranus and Neptune is called Voyager 2, even though it carried the fuller version of the Grand Tour. History often preserves these practical decisions after their original reasons have faded. Both launches also belong to a narrow window. The planets were moving whether NASA was ready or not. A delay of months would not simply inconvenience the mission. It could close the geometry that made the whole trajectory possible. This is one of the pressures that makes planetary exploration so different from many Earth-based projects. The launch date is not just a management target. It is written into celestial mechanics. Once launched, each spacecraft began as something very fast by human standards and very slow by interstellar standards. It escaped Earth, crossed the orbit of Mars, passed through the asteroid belt, and approached Jupiter after months of cruise. Even at tens of thousands of kilometers per hour, the distances were already large enough to force a different relationship with time. Commands were planned long before execution. Navigation updates depended on radio tracking. Small errors, if left uncorrected, could grow into planetary-scale misses. Voyager was therefore never a simple straight flight. It was a continuing act of correction. Measure the spacecraft's path, compare it with the desired trajectory, fire thrusters briefly, measure again, refine again. The romance of the mission is real, but underneath the romance is navigation discipline. The engineering behind the Voyager spacecraft was a reflection of the state of the art in 1970s technology. The guidance and control computers operated with the processing power of a modern pocket calculator. Data storage was on digital tape recorders, physical magnetic tape, stored in loops, recorded, and played back for transmission to Earth. Power came from radioisotope thermoelectric generators, devices that convert the heat from the radioactive decay of plutonium-238 into electrical power, not through any moving mechanical parts, but directly through the Seebeck effect. This choice of power source, nuclear rather than solar, was essential for a mission to the outer solar system where sunlight is too dim to drive solar panels of any practical size. The communications system was built around a high-gain dish antenna 3.7 meters in diameter, carefully pointed at Earth using the spacecraft's attitude control thrusters. The transmitter power was just 23 watts, comparable to a household light bulb, and yet the signals, carried on X-band radio frequencies, could be detected by the large receiving antennas of NASA's Deep Space Network across billions of kilometers. The feat of receiving 23 watts of transmitted power after it has spread and attenuated over cosmic distances is made possible by the size of the receiving antennas, dishes up to 70 meters in diameter, and by the extremely low noise electronics of the receiving systems. Even so, the data rate achievable over interplanetary distances is far lower than what any modern terrestrial communication system achieves, and managing this constraint has been one of the continuous engineering challenges of the Voyager mission. The spacecraft themselves were built for autonomy because they had to be. At Jupiter and Saturn, the distance from Earth already made real-time control impossible. At Uranus and Neptune, the delay was so long that the spacecraft needed to execute carefully prepared sequences on its own. Turn, point, expose, record, transmit, protect itself, and continue. The cameras had to point at moons moving rapidly through the field of view during high-speed flybys. The scan platforms had to compensate for spacecraft motion. The tape recorders had to store data when the transmission rate was too low to send everything live. The attitude control system had to keep the high-gain antenna pointed precisely enough at Earth for the Deep Space Network to hear a signal that had become almost unimaginably faint. This is easy to underestimate because Voyager images now feel familiar. We see Io's volcanoes, Saturn's rings, Uranus's moons, Neptune's storms, and Triton's terrain as if they were simply photographed. But every one of those images was the result of navigation, timing, exposure planning, instrument pointing, data storage, downlink scheduling, error correction, and reconstruction on Earth. The spacecraft did not drift past the planets taking casual snapshots. It executed a dense, carefully rehearsed choreography under severe limits of memory, power, pointing, and time. Even the slow data rates shaped the science. Mission teams had to decide which images mattered most. They had to choose filters, exposure times, target priorities, and downlink sequences. Some data would be transmitted immediately. Some would be recorded on tape and played back later. Some desired observations would not fit. A planetary flyby is brief, and the spacecraft cannot stop. Once Voyager passed a moon, the geometry was gone forever. This gives the Voyager planetary encounters a special intensity. There were no second passes, no orbit insertion, no years of mapping. Just approach, closest encounter, departure, and the irreversible fading of the target behind the spacecraft. Every successful observation was a recovered moment from a moving machine. The actual encounter days must have felt unlike ordinary science. A spacecraft approaches for years, and then the most important hours pass quickly. The data begin arriving, but delayed by light travel time. Images appear line by line, frame by frame, on monitors and printouts. Scientists see surfaces no one has seen before and have to interpret them almost immediately while more data are still coming. A plume on Io is first a strange feature, then an eruption. A ring gap is first a line, then evidence of a moon or resonance. A moon's surface is first a pattern, then a geological history. There is a particular kind of pressure in first encounters. You are not only collecting data, you are updating humanity's picture of a world in real time. A wrong first interpretation may become famous. A small feature may matter more than it first appears. The target will soon be receding, and the spacecraft cannot turn around. This makes the Voyager encounters feel almost theatrical, but the theater was built from math and engineering. Years of preparation delivered a few days of revelation. The instrument package was designed to make each flyby more than a photograph. The images returned by Voyager also changed how the public imagined the outer solar system. Before Voyager, most people had never seen the outer planets as places. There were telescopic images, artist impressions, diagrams, and grainy earlier spacecraft views, but the moons were still largely abstract. Voyager made them physical. It showed ridges, plumes, craters, ring shadows, cloud bands, storms, haze, ice, and strange terrains that looked neither Earth-like nor entirely alien in any simple way. This visual transformation matters because science advances through measurement, but human imagination often advances through images. An image can make a target real enough to care about. Europa's cracked surface is a scientific clue, but it is also an invitation. Triton's geyser streaks are data, but they also make a distant moon feel like an active world. Saturn's rings, resolved into thousands of structures, made the word ring feel suddenly inadequate. Voyager's cameras did not only show what was there, they changed what future missions seemed worth doing. A moon that looks like a point of light may be interesting. A moon with volcanoes, fractures, possible oceans, or strange terrains becomes a destination. In that sense, Voyager turned the outer solar system from a map into a landscape. The imaging system produced the pictures that became famous, but the cameras were only part of the scientific payload. The magnetometers measured planetary magnetic fields and the magnetic environment carried by the solar wind. Plasma and charged particle instruments measured electrons, ions, and energetic particles. The ultraviolet spectrometer studied atmospheres and auroras. The infrared interferometer spectrometer measured heat and composition. The photopolarimeter helped study rings and atmospheres by measuring how light was scattered and polarized. The radio science system used changes in the spacecraft's radio signal to probe atmospheres, ring particles, gravity fields, and plasma between the spacecraft and Earth. This matters because the Voyager discoveries were not made by images alone. Titan's surface was hidden from the cameras, but radio and infrared measurements revealed the atmosphere's structure. Planetary magnetospheres were invisible to the cameras, but vivid to fields and particles instruments. The heliopause was not photographed. It was detected through plasma waves, particle changes, and magnetic field measurements. The outer solar system became understandable because Voyager carried many senses, not only eyes. A spacecraft instrument is a way of asking a question. A camera asks what the surface looks like. A magnetometer asks where charged particles will move. A plasma instrument asks what kind of gas surrounds the spacecraft. A radio science experiment asks how a signal is bent, delayed, absorbed, or shifted as it passes through an atmosphere or ring system. Together, they turn a flyby into a physical investigation. The most interesting thing about Voyager's design is how little margin it had by modern standards and how much science it returned anyway. The memory was small. The data rates were low. The processors were simple. The cameras were limited compared with later planetary instruments. But the mission was designed around those limits, and the limits forced discipline. The spacecraft did not need to be modern. It needed to be reliable, predictable, and useful in the specific windows when the planets would pass before it. The first major planetary encounter of the Voyager program was Jupiter, and both spacecraft transformed our understanding of the solar system's largest planet in the few months surrounding their respective closest approaches. Voyager 1 reached Jupiter on March 5, 1979, making its closest approach at a distance of about 348,000 kilometers from the cloud tops, close enough to resolve fine-scale structure in Jupiter's clouds and to examine the planet and its moons with unprecedented detail. Voyager 2 followed on July 9, 1979, with a different trajectory that took it closer to several of the major moons. The Jupiter encounters produced a torrent of discoveries, several of them completely unexpected. The most dramatic was the discovery of active volcanoes on Io. Before Voyager, the 4 Galilean moons, Io, Europa, Ganymede, and Callisto, had been observed as points of light from Earth, with spectroscopic hints of their compositions, but no surface detail. The geological state of Io's surface was entirely unknown. When Voyager 1's cameras resolved Io and began returning images, the science team saw a surface unlike anything in the solar system. Not a heavily cratered, ancient landscape like the Moon or Mercury, but a smooth, oddly colored terrain painted in yellows, oranges, and whites, with no obvious impact craters at all. The absence of craters was puzzling. It implied that Io's surface was being continuously refreshed, erasing craters faster than they could accumulate. But what mechanism could be responsible? The answer arrived before anyone had thought to look for it. Navigation engineer Linda Morabito, processing images to refine the spacecraft's trajectory, noticed in one photograph what appeared to be an anomalous bright feature off the limb of Io, a plume extending above the surface. Looking more carefully, the team identified it as a volcanic eruption, a plume of material being ejected from Io's surface to heights of several hundred kilometers. Further examination of the images revealed multiple simultaneous volcanic eruptions across Io's surface. It was the first time active volcanic activity had been directly observed on any world other than Earth. The mechanism behind Io's volcanism was rapidly identified as tidal heating, the constant flexing of Io's interior by the competing gravitational pulls of Jupiter, Europa, and Ganymede, which keeps Io in a slight but changing elongation that generates internal heat through tidal friction. This process was actually predicted in a paper published just 3 days before Voyager 1's closest approach by Stanton Peele, Patrick Casson, and Ray Reynolds, who had worked out the implications of the tidal heating mechanism for Io, one of the more remarkable instances of a theoretical prediction and observational confirmation arriving almost simultaneously in the history of planetary science. Europa, the second Galilean moon inward, presented an entirely different and equally surprising surface. Rather than Io's volcanic landscape, Europa showed a surface of nearly pure water ice, extraordinarily smooth and almost completely free of large impact craters, crisscrossed by a complex network of long, curved lines and bands. The smoothness and youth of Europa's surface implied recent or ongoing resurfacing. Something was continuously renewing Europa's icy exterior. The leading interpretation was that Europa harbors a global subsurface ocean of liquid water beneath its ice shell, maintained at liquid temperatures by tidal heating, with the ice shell above being warm enough to deform and flow, erasing impact craters as they form and producing the complex surface texture of ridges and bands. This interpretation, that Europa might have a subsurface ocean, had profound implications for the search for life, as discussed in the Are We Alone episode. The discovery was not definitive from Voyager data alone, but it was compelling enough to motivate future missions specifically designed to investigate Europa, and it established the Moon as one of the highest priority targets for astrobiology in the solar system. Ganymede, the largest moon in the solar system, showed a surface divided between ancient, heavily cratered dark regions and younger, lighter regions etched with grooves and ridges, suggesting a history of geological activity. Callisto, farthest from Jupiter and experiencing the least tidal heating, appeared almost entirely covered in ancient craters, a dark, complex surface preserving one of the most detailed records of the early solar system's bombardment available anywhere. Jupiter itself revealed atmospheric dynamics of extraordinary complexity. The Great Red Spot, known since the 17th century as a prominent feature in Jupiter's clouds, was resolved in detail and found to be an enormous anticyclonic storm, rotating counterclockwise, with wind speeds at its margins of several hundred kilometers per hour. Time-lapse sequences assembled from successive images showed the storm rotating over the course of days, with turbulent wake patterns visible downstream in the cloud field. The alternating cloud bands of Jupiter, the light zones and dark belts, showed complex, dynamic structure with jet streams, smaller storms, and interacting vortices visible throughout the cloud layer. Voyager 1 also discovered that Jupiter has rings, a thin, faint ring system completely invisible from Earth, but detectable in the backlit geometry available as Voyager looked back toward Jupiter after closest approach. The rings are composed of fine dust, dark and diffuse, fed by micrometeorite impacts on the small inner moons, and completely different in character from Saturn's brilliant, icy ring system. The Jupiter system also produced one of the most spectacular auroral phenomena ever observed away from Earth. Jupiter's powerful magnetic field, generated by the deep metallic hydrogen in its interior, traps charged particles from the solar wind and from Io's volcanic emissions into intense radiation belts, and these particles spiral into Jupiter's polar regions along magnetic field lines, generating aurora orders of magnitude more powerful than Earth's northern lights. Voyager instruments detected the electromagnetic signatures of these processes, documenting a magnetosphere so vast that if it were visible from Earth, it would appear larger than the full moon. The Jupiter encounter also changed the way scientists thought about moons. Before Voyager, moons were often imagined as secondary objects, smaller companions, interesting but subordinate to the planets they orbited. Jupiter overturned that hierarchy. Io, Europa, Ganymede, and Callisto were not simply 4 satellites. They were 4 worlds, each with a distinct geological identity. Io was volcanic. Europa was icy and possibly ocean-bearing. Ganymede was grooved and differentiated. Callisto was ancient and cratered. In one planetary system, Voyager found a sequence of internal heating, resurfacing, ice, rock, cratering, and possible habitability. That discovery reshaped planetary science. It made clear that a moon does not need to be near the sun to be active. Energy can come from tides. Worlds far from the habitable zone can have liquid water inside them if gravitational flexing supplies heat. The outer solar system, once imagined as a cold collection of inert bodies, became a place of active geology and potential subsurface oceans. This is one reason Voyager remains scientifically alive in modern missions. Galileo, Cassini, Juno, Europa Clipper, JUICE, Dragonfly, and proposed ice giant missions all inherit questions Voyager sharpened. It did not answer everything. It revealed what the right questions were. Io and Europa are a useful pair because together they showed 2 faces of tidal heating. Io is the extreme visible case. Its surface is remade by volcanism so often that impact craters cannot survive. Sulfur and sulfur dioxide frost create the strange yellows, oranges, whites, and blacks seen in Voyager images. Volcanoes throw material hundreds of kilometers high. The moon is squeezed by Jupiter's gravity and by orbital resonance with Europa and Ganymede, flexing its interior and turning orbital energy into heat. It is a world kept alive by gravity. Europa is quieter on the surface, but perhaps more profound. Voyager did not directly measure an ocean, but it showed a surface that made an ocean plausible. Bright ice, few craters, long lineae, bands, ridges, and a surface young enough to imply renewal. Later missions and observations built on this foundation, but the first step was Voyager's revelation that Europa was not a dead ice ball. It was a smooth, fractured, geologically young world. The contrast mattered. Io showed that tidal heating could produce the most volcanic body known. Europa suggested that tidal heating could help maintain liquid water beneath ice. The same gravitational system produced both fire and ocean. That idea changed how scientists think about habitability because it separated liquid water from sunlight. A world could be far from the sun and still be interesting for life if internal heat, chemistry, and water existed together. This is the kind of conceptual shift that makes Voyager's discoveries larger than the images themselves. The spacecraft did not merely add details to known moons. It changed the range of worlds that seemed scientifically possible. Jupiter itself was also a lesson in scale and motion. A still image of Jupiter can make the planet look almost painted. Bands, zones, swirls, ovals, and the great red spot arranged in a pattern that seems decorative. Voyager's time-lapse sequences made clear that the atmosphere is not a painting. It is moving. Clouds shear past one another. Small storms rotate. Jet streams maintain sharp boundaries between belts and zones. The Great Red Spot is not a red mark, but a rotating atmospheric system larger than Earth, embedded in a turbulent field of smaller vortices. The atmospheric physics is different from Earth's because Jupiter has no solid surface in the way Earth does. Its weather is deep, fast, and driven by internal heat as well as sunlight. The visible clouds are only the upper part of a much deeper fluid planet. Voyager could not see to Jupiter's center, but it showed enough motion to make the planet feel alive in a meteorological sense. The faint ring discovery also changed assumptions. Saturn was the ringed planet in public imagination. Voyager showed that Jupiter, too, had rings, dark, thin, dusty, and easy to miss. Later, Uranus and Neptune were also confirmed to have ring systems. Rings were not a Saturnian exception. They were a broader feature of giant planet systems, expressed differently depending on moons, impacts, dust, ice, and gravitational resonances. This is another pattern in Voyager's legacy. It turned uniqueness into families. Jupiter had rings. Outer moons could be geologically active. Ice giants had strange magnetic fields. The solar system became less a set of isolated oddities and more a set of related systems with variations. After Jupiter, both Voyagers were directed towards Saturn, Voyager 1 arriving in November 1980 and Voyager 2 in August 1981. The Saturn encounters produced another cascade of discoveries, again with several that were entirely unexpected. Saturn's ring system, already known to be complex from Earth-based observations, was revealed in stunning detail. Where Earth-based telescopes could resolve the broad A, B, and C rings and the Cassini division, Voyager cameras showed thousands of individual ringlets within each main ring, organized into a complex, finely structured system unlike anything in earlier planetary science. The B ring, the densest and most prominent, showed not just thousands of ringlets, but mysterious spokes, radial features extending across the ring plane that appeared and disappeared over hours, apparently associated with electromagnetic effects acting on very small dust particles within the ring. The F ring, discovered just outside the main rings, showed a narrow, braided structure maintained by two small shepherd moons, Prometheus and Pandora, orbiting just inside and outside it, whose gravitational influence confined and shaped the ring in ways that produced the kinked, complex morphology visible in Voyager images. The discovery of new moons was another major result of the Saturn encounters. Prior to Voyager, Saturn was known to have 10 moons. The Voyager encounters increased this count to 17, with 7 new moons discovered in or near the ring system. Several of these, including Prometheus, Pandora, Atlas, Pan, and others, are small, irregularly shaped bodies deeply embedded in the ring system, whose orbits and gravitational interactions shaped the ring structure in ways that were still being worked out for years after the flyby. Titan, Saturn's largest moon, and already known from Earth-based spectroscopy to have a thick nitrogen atmosphere, unique among solar system moons, was a particular target of both Voyager visits. Voyager 1's trajectory was specifically designed to make a close flyby of Titan, sacrificing the option to continue to Uranus and Neptune for the priority of examining Saturn's most scientifically interesting moon. The Titan flyby brought the spacecraft within 6,490 kilometers of the moon's surface, the closest approach of either Voyager to any solar system body. But the thick orange haze filling Titan's atmosphere blocked all camera views of the surface entirely. The cameras returned images of a smooth, featureless orange orb, giving no information about the landscape beneath. The infrared instruments, however, measured temperatures and vertical atmospheric structure, and the radio science measurements as Voyager's signal passed through Titan's atmosphere on its way to Earth provided information about the atmospheric density and composition profile that confirmed Titan as a world of extraordinary chemical complexity. The surface and interior of Titan remained mysterious until the Cassini-Huygens mission 3 decades later. But Voyager's confirmation of the thick nitrogen atmosphere, the detection of numerous organic molecular species in the atmosphere using the ultraviolet spectrometer, and the measurement of the atmospheric pressure and temperature profile established Titan as one of the most scientifically important bodies in the solar system and directly motivated the development of the Cassini mission. The Saturn encounter also provided an early opportunity to observe the planet's magnetosphere, polar auroras, and radio emissions, and to begin characterizing the physical properties of the outer icy moons. Mimas, Enceladus, Tethys, Dione, Rhea, and Hyperion in detail that Earth-based observations could not provide. Enceladus, in particular, showed an unusually young and smooth surface reminiscent of Europa, suggesting active resurfacing, the first hint of what Cassini would later dramatically confirm as active plume eruptions from the Moon's south pole. Saturn also taught a lesson about rings that went far beyond beauty. A ring system is not a flat, passive disk. It is a gravitational laboratory. Particles orbit at different speeds depending on distance. Moons open gaps, confine edges, stir waves, and sculpt narrow strands. Resonances create patterns. Tiny particles respond to electromagnetic forces. Impacts grind material down and spread dust. The whole structure is thin, bright, dynamic, and temporary on long timescales. Voyager revealed that Saturn's rings were not smooth bands, but a system of astonishing fine structure. The rings contained waves, ringlets, gaps, spokes, edges, braids, and shepherded features. This complexity later became one of Cassini's great scientific themes, but Voyager made the first close-up revelation. The rings were not simple. The same was true of Saturn's moons. Mimas carried a crater so large it made the moon look almost broken. Iapetus had a dramatic brightness contrast between leading and trailing hemispheres. Hyperion was irregular and chaotic looking. Enceladus appeared unexpectedly smooth in places, hinting at a resurfaced world long before Cassini discovered its active south polar plumes. Titan was hidden by haze, but that hiding was itself a discovery. A moon with an atmosphere thick enough to conceal a surface from one of humanity's best cameras. Voyager did not solve Titan. It made Titan unavoidable. Titan deserves special attention because Voyager's partial failure to see its surface was itself scientifically productive. A camera pointed at Titan returned haze. The surface did not appear. In another mission, that might have been a disappointment. But haze is information. A thick, orange, photochemical atmosphere means that sunlight is breaking apart methane and nitrogen chemistry in the upper atmosphere, allowing complex organic molecules to form and accumulate. Titan was not merely hidden. It was chemically active. The idea of Titan as a prebiotic chemistry laboratory grew from this kind of evidence. It has liquid methane and ethane on the surface, a nitrogen-rich atmosphere, organic haze, weather, clouds, and a surface shaped by processes that resemble Earth in form while using different materials. Voyager could not see the lakes and rivers that Cassini-Huygens later revealed, but it confirmed the thick atmosphere and made the case that Titan was not just another moon. Voyager 1's close Titan flyby was therefore worth the sacrifice. It ended that spacecraft's grand tour path, but it elevated Titan into the first rank of planetary targets. Decades later, Cassini carried the Huygens probe to Titan's surface. In the future, Dragonfly is intended to fly through Titan's atmosphere and study its organic-rich landscape directly. Voyager did not complete Titan's story. It opened it. After Saturn, Voyager 1's trajectory, shaped by its Titan flyby, carried it out of the plane of the solar system, headed northward above the ecliptic on a trajectory toward interstellar space. There would be no further planetary encounters for Voyager 1. Its remaining mission would be a long journey outward, monitoring the interplanetary medium and eventually the heliospheric boundary, until the power supplies failed. Voyager 2, having taken a somewhat different trajectory that preserved the option of continued planetary encounters, was directed toward Uranus after its Saturn flyby. This required a gravity assist from Saturn that angled the spacecraft's trajectory precisely toward Uranus, a trajectory designed more than 4 years in advance, calculated and recalculated as the Saturn encounter refined knowledge of Saturn's gravitational field. Voyager 2 reached Uranus in January 1986. It was the first spacecraft ever to visit the ice giants, and its encounter with Uranus, as discussed in the Uranus episode, was brief and strange. The planet's extreme axial tilt meant the solar system looked fundamentally different from any other planetary encounter. The spacecraft was approaching essentially from above the pole of the planet and its moon system, rather than from the side as for Jupiter and Saturn. The moons appeared to orbit in nearly circular patterns around the pole, and the planet's rings appeared as concentric circles. The Uranus encounter lasted only a few days at close range, with closest approach to the planet on January 24, 1986, the day, by an unfortunate coincidence, that the Space Shuttle Challenger was destroyed 73 seconds after launch, killing all 7 crew members. The disaster dominated news coverage that day, and the Voyager 2 Uranus results, extraordinary in their own right, were somewhat overshadowed. The encounter revealed Uranus as a featureless, nearly uniform blue-green disk with essentially no obvious cloud structure at visible wavelengths, dramatically different from the banded, dynamic atmospheres of Jupiter and Saturn. The magnetic field was found to be dramatically tilted, about 60 degrees from the rotation axis, and significantly offset from the planet's center, a configuration unlike any other planetary magnetic field, and suggesting that the dynamo generating it operates in the conducting mantle rather than in the core. 10 new moons were discovered, and the rings were directly imaged for the first time, confirming and extending the 1977 occultation discovery. The flyby of Uranus's major moons provided the first close-up views of these worlds, revealing Miranda's extraordinary geological complexity, cliffs, coronae, and mixed terrain that defied simple explanations, and the varied states of the other moons from the geologically active appearing Ariel to the ancient, cratered Umbriel and Oberon. After Uranus, Voyager 2 was directed toward Neptune, the final destination of the Grand Tour, reached in August 1989. The Neptune encounter was, in many ways, the most scientifically productive of the 4 planetary visits. Neptune, unlike Uranus, showed a vivid, dynamically active blue atmosphere with distinct cloud features including the Great Dark Spot, an anticyclonic storm roughly the size of Earth, and the rapidly moving bright feature nicknamed Scooter by the mission team. The atmosphere proved far more active than expected, with wind speeds reaching 2,000 kilometers per hour, the fastest measured on any planet. The magnetic field at Neptune showed the same dramatic tilt and offset as at Uranus, confirming that this unusual magnetic configuration is a characteristic feature of ice giant planets rather than a peculiarity of Uranus alone. Neptune's ring system was directly imaged, confirming the ring arcs, confined bright segments within the outer Adam's ring, that had been inferred from Earth-based stellar occultation observations and whose confinement by the shepherd moon Galatea was confirmed. 6 new moons were discovered, and Triton, Neptune's large, retrograde moon, was examined for the first time with any imaging instrument capable of resolving its surface. The images revealed a world unlike any other in the solar system, the cantaloupe terrain of the southern hemisphere, the active nitrogen geysers erupting from the south polar cap and leaving dark streaks across the frozen surface, and evidence for a geologically recent resurfacing that implied some form of internal activity driven by the unusual tidal forces resulting from Triton's retrograde orbit. The temperature of Triton's surface, minus 235 degrees Celsius, only 38 degrees above absolute zero, was the lowest surface temperature measured anywhere in the solar system at the time. The Neptune encounter ended on August 25, 1989, the last planetary flyby of the Voyager mission. After Neptune, Voyager 2 joined Voyager 1 on a trajectory out of the solar system, heading southward below the ecliptic while Voyager 1 continued northward. The ice giant encounters are especially valuable because they remain lonely. Jupiter has been visited by multiple spacecraft. Saturn was orbited for 13 years by Cassini. Uranus and Neptune, by contrast, have been seen close up only once by Voyager 2 during brief flybys. Almost everything we know at high resolution about their moons, rings, magnetic fields, and close atmospheric structure begins with those few days in 1986 and 1989. This gives the Voyager 2 ice giant data an unusual status: old, limited, sometimes noisy by modern standards, and still irreplaceable. Uranus and Neptune are also not minor variations of Jupiter and Saturn. They are a different class of planet. Their interiors are dominated not by hydrogen and helium alone, but by water, ammonia, methane, and other volatile compounds under extreme pressure, in forms that do not behave like ordinary ice or ordinary gas. Their magnetic fields are tilted and offset, suggesting dynamos operating in shells or layers rather than in a simple central metallic region. Their atmospheres are cold, but not meteorologically dead. Neptune, despite receiving far less sunlight than Uranus, displayed stronger winds and more visible atmospheric activity. This remains one of the open puzzles of the outer solar system. Why is Uranus so muted in Voyager's visible images while Neptune is so active? How much of that difference was seasonal timing? How much reflects internal heat? How do ice giant dynamos really work? What are the histories of Miranda, Ariel, Triton, and the other moons? Voyager gave the first answers, but it also left a strong argument for returning. Every modern discussion of a Uranus orbiter or Neptune mission begins in the shadow of Voyager 2. The spacecraft flew past once. The questions remained. Miranda became one of the strangest small worlds in the Voyager archive. Its surface appears almost stitched together. Old cratered regions beside younger grooved terrain, enormous fault scarps, polygonal coronae, and cliffs whose scale is astonishing for such a small moon. The exact explanation remains debated. Miranda may have been reshaped by tidal heating, orbital resonances, partial differentiation, or catastrophic disruption and reassembly. The images are limited because Voyager saw only part of the moon well, but that limitation makes the mystery sharper. A small icy moon at Uranus should have been simple. It was not. Triton was even more surprising. Its retrograde orbit means it almost certainly did not form around Neptune in place. It was likely captured, perhaps from the Kuiper belt. Capture would have been violent, reshaping the original Neptunian moon system and heating Triton through tidal interactions. Voyager found a young surface, few craters, strange terrains, and dark streaks from active plumes. At the cold edge of the planetary system, Triton was still changing. This made Triton a bridge between worlds Voyager had seen and worlds it had not. Its composition and likely origin connected it to Pluto and the Kuiper belt, which would not be visited until New Horizons flew by Pluto in 2015. In a sense, Voyager 2's Triton encounter was humanity's first close look at a captured Kuiper belt-like world, decades before the Kuiper belt became a central region of planetary science. The ice giant flybys, therefore, did something no other mission has repeated. They gave one fast glimpse of a class of planets and moons that remains mostly unexplored. The data are old, but the questions are current. There is one image from the Voyager program that stands apart from all the others, not because of what it shows, but because of what it means. It was taken by Voyager 1 on February 14, 1990, more than 12 years after launch, at the suggestion of Carl Sagan. By that date, Voyager 1 had traveled about 6 billion kilometers from Earth, farther than any human-made object had been before. It was drifting outward at about 17 kilometers per second, already far beyond the orbit of Neptune, heading toward interstellar space. The cameras had been switched off months earlier. They served no scientific purpose at such extreme distances and in the deep dark beyond the planets. And the spacecraft was focused on its continuing measurement of the interplanetary plasma and magnetic field. Sagan had been asking NASA to turn the cameras back on one final time, for one final purpose: to look back toward the inner solar system and photograph the planets from Voyager's extraordinary vantage point. The proposal had been resisted by some NASA managers who worried about damaging the cameras by pointing them too close to the sun and who considered the scientific value minimal. Sagan persisted. He won. On February 14, 1990, Voyager 1 turned its cameras back toward the sun and photographed the solar system from the outside, the first time any human-built device had done so. The resulting mosaic, assembled from 60 frames, showed the sun and several planets as faint points of light against a field of scattered sunlight. Earth appeared as a tiny dot, less than a pixel in size in the original images, a pale, almost indistinguishable point in a sunbeam, barely distinguishable from the camera's optical artifacts. Sagan gave the image its name, the pale blue dot. Later, reflecting on what it showed, he turned the photograph into one of the most famous meditations on scale in modern science. Earth as a tiny point, almost lost in scattered sunlight, carrying every human life, every country, every argument, every ambition, every memory, and every hope that had ever existed. The pale blue dot photograph does not contain any technical discovery. It does not reveal any new physical phenomenon or measure any astrophysical quantity. What it does, and what Sagan understood it would do, is provide a perspective, a visceral, visual demonstration of the actual scale relationship between Earth and the cosmos. Looking at the image, feeling the truth of it rather than merely knowing it abstractly, is one of the most quietly transformative experiences available to anyone who takes the time to think about what they are looking at. The Voyager scientists and engineers had been working for 12 years to explore the outer solar system. Sagan wanted to give them, and all of humanity, one more thing: a picture of home from the far side of the solar system, to help understand what home actually is and where it fits in the larger story of the cosmos. The pale blue dot also matters because it is one of the rare space images whose power comes from absence. Most famous space images impress us by revealing detail: the spiral arms of a galaxy, the clouds of Jupiter, the rings of Saturn, the pillars of a nebula. The pale blue dot does the opposite. It removes detail. It shows Earth as almost nothing. No borders, no oceans, no faces, no cities, no evidence of language, conflict, memory, ambition, grief, or love. The image works because everything human has been compressed into a point too small to resolve. That compression is scientifically ordinary and emotionally enormous. From 6 billion kilometers away, Earth is not visually important. It is not central. It is not large. It is not obviously inhabited. It is one dot among scattered light. And yet from that dot came the spacecraft that took the picture, the radio antennas that received it, the people who understood it, and the impulse to look back. Voyager's planetary images expanded the solar system. The pale blue dot reduced us to scale. Both were necessary. Sagan's reflection on the pale blue dot has become famous partly because it gave language to something the image itself refused to show. The photograph contains no visible humanity, but the words restore human scale to the dot. All lives, all histories, all arguments, all hopes, all cruelty, all tenderness, all of it on one tiny point. The image is not sentimental by itself. It is almost brutally unsentimental. The sentiment enters when the viewer understands what the point contains. This is why the pale blue dot remains useful. It is not an argument against ambition, exploration, or human seriousness. It is an argument against forgetting scale. The image does not make human life meaningless. It makes it concentrated. Everything we know, value, build, fear, and love is local. Voyager, by leaving, showed us the locality. That is a rare kind of scientific image, one that increases both humility and responsibility. Before the Voyager spacecraft were launched, a decision was made that transformed both missions from purely scientific endeavors into something larger and stranger and more difficult to categorize. The decision to include a message. The Voyager Golden Record is a 12-inch gold-plated copper disc, one of which was attached to each spacecraft, enclosed in an aluminium cover engraved with diagrams indicating how to construct a device to play the record and how to interpret its contents. The record was the product of a committee chaired by Carl Sagan, which included Andrew Yen, John Lomberg, and Frank Drake, among others. Their charge was to create a greeting from Earth to whatever intelligence might, in the unimaginably distant future, encounter the spacecraft. The record contains 115 images, encoded digitally, diagrams of Earth's location relative to pulsars, mathematical and physical definitions, images of Earth's chemistry, anatomy, geography, flora, fauna, and human life in its diversity. It contains spoken greetings in 55 languages, from Akkadian to Wu Chinese. It contains a sequence of sounds of Earth, waves, wind, thunder, animals, a human heartbeat, the sound of a rocket launching, a child crying, footsteps. And it contains 55 minutes of music: Bach, Beethoven, Mozart, Stravinsky, Chuck Berry's Johnny B. Good, Blind Willie Johnson's Dark Was the Night, Cold Was the Ground, traditional music from Bulgaria, Azerbaijan, Peru, Senegal, Australia, and a dozen other traditions. The music selection was made by a committee that worked urgently. The launch windows were fixed and immovable, and the record had to be completed in time. And Andrew Yen, who was serving as the creative director of the project, fell in love with Carl Sagan during the record's production, a fact she later described as one of the great privileges of her life, in which she commemorated by arranging to have her brainwaves recorded and included on the record, a sonic representation of a human brain in a state of love and wonder, included among the images and sounds to represent something difficult to describe through pictures or conventional language. The Golden Record was designed to last for billions of years in the cold, radiation-sparse environment of interstellar space. Gold does not corrode. Copper protected by gold does not corrode. The record is protected from micrometeorite damage by its aluminium cover. The diagrams engraved on the cover are meant to be self-explanatory enough that any intelligence capable of constructing a playback device could recover the images and sounds. Whether any intelligence will ever find either Voyager spacecraft is a question that can be answered with simple mathematics and a fairly bleak probability estimate. Even at Voyager 1's current velocity of about 17 kilometers per second, roughly 60,000 kilometers per hour, it would take approximately 70,000 years to reach the distance of the nearest star, Proxima Centauri, if it were aimed in that direction, which it isn't. It will in fact pass within about 1.6 light-years of the star Gliese 445, also known as a C+ 793888, in roughly 40,000 years, and within a few light-years of other nearby stars over much longer timescales. In several million years, it will have drifted through a portion of the Milky Way far from where it is now. The probability that any specific intelligent civilization will ever encounter either Voyager, searching through the enormous volume of interstellar space, is essentially infinitesimal on any timescale relevant to human concerns. The Golden Record is not, in any practical sense, a message that expects a recipient. It is something else, a gesture, perhaps, or a statement, or an act of self-definition. A civilization that is willing to spend significant resources producing a detailed, careful, beautiful representation of everything it considers most worth sharing about itself, and then launching it into the dark with no expectation of response, is expressing something important about what it values and what it believes matters. Carl Sagan described the golden record as a gift to the cosmos, and as a way of saying, for whatever audience might eventually receive it, or for no audience at all, that Earth existed, that it was inhabited, that the inhabitants made music and looked at stars and wondered about the universe. The golden record can be misunderstood if it is treated only as an attempt to communicate with aliens. Of course it is that, in a formal sense. It contains instructions. It contains information. It contains a map-like reference using pulsars. It contains images and sounds arranged with the hope that an intelligence capable of finding the spacecraft might also be capable of decoding the message. But the chances of discovery are so small that the record's practical function is almost secondary. Its deeper function may be internal. It forced human beings to ask what Earth should say if it had one small chance to introduce itself. Not to advertise, not to conquer, not to demand. Simply to say, this is where we are, this is what we look like, these are some of the sounds of our world, this is some of the music we have made, this is how we tried to understand mathematics, biology, and the sky. That act of selection is revealing. A civilization can be described by what it chooses to send when no reply is expected. The golden record included science, but also music. It included anatomy, but also laughter. It included greetings, but also thunder, waves, birds, footsteps, and a heartbeat. It did not try to present Earth as perfect. It tried to present Earth as alive. That may be why the record remains emotionally powerful even for people who know it will almost certainly never be heard. It is a message outward, but also a mirror inward. It asks, if this were the only trace of us, would it be kind? Would it be honest? Would it be beautiful? The instructions on the golden record cover are themselves a remarkable artifact. They try to communicate without a shared language. A drawing of the hydrogen atom gives a basic time and length reference. Pulsar positions give a way, in principle, to identify the sun's location and epoch because pulsars are natural clocks whose periods slowly change over time. Diagrams show how the record should be played and how the images are encoded. The designers had to imagine an intelligence that could understand physics but not human conventions, an intelligence capable enough to find and examine a spacecraft, but unfamiliar with Earth, English, music notation, or the assumptions built into human culture. That problem is almost impossible. Every message assumes something. A diagram assumes geometry can be interpreted. A sequence assumes order can be recognized. A map assumes the recipient knows what kind of object the marks represent. The golden record is therefore not a perfect universal language. It is an attempt, carefully made, to reduce the dependence on local culture and lean on physics as much as possible. This makes the record scientifically humble. It does not say, "You will understand us." It says, "We have tried to make ourselves understandable." That difference matters. The scientific mission of Voyager did not end with the planetary encounters. As both spacecraft traveled outward through the outer solar system, they continued measuring the interplanetary plasma, magnetic field, and energetic particle environment, monitoring the properties of the solar wind at progressively greater distances from the Sun. This extended mission, the Voyager Interstellar mission, begun formally in 1990, is investigating the outer boundary of the heliosphere and the nature of the transition from the solar wind's domain to the interstellar medium. The heliosphere is the bubble carved out by the solar wind in the surrounding interstellar medium. Solar wind particles flow outward from the Sun at hundreds of kilometers per second, maintaining their dominance over the interstellar medium out to a distance of roughly 100 to 150 astronomical units, where the ram pressure of the solar wind is balanced by the pressure of the interstellar medium. The outer boundary of the solar wind's direct domain, the heliopause, is where the solar wind plasma is replaced by the plasma of the interstellar medium. Between the Sun and the heliopause, several distinct structural features of the heliosphere exist. The termination shock, at roughly 80 to 100 astronomical units, is where the supersonic solar wind slows abruptly to subsonic speeds as it encounters the increasing resistance of the surrounding interstellar pressure. Beyond the termination shock is the heliosheath, a turbulent region of slowed, compressed solar wind where the solar and interstellar plasmas interact. At the heliopause, the solar wind's plasma is replaced by the interstellar medium's plasma, and the Sun's magnetic field, carried outward by the solar wind in the Parker spiral pattern, is replaced by the magnetic field of the interstellar medium. Voyager 1 crossed the termination shock in December 2004, detecting the expected increase in plasma density and magnetic field strength as it entered the heliosheath. It spent the next 8 years traversing the heliosheath, encountering a surprisingly turbulent and magnetically complex environment that did not quite match the predictions of heliospheric models developed before the measurement was available. In August 2012, Voyager 1 crossed the heliopause and entered interstellar space, becoming the first human-made object to do so. The crossing was identified through a dramatic and sudden change in the plasma environment. The density of plasma particles jumped sharply from the low density of the solar wind to the somewhat higher density of the local interstellar medium, while the energy spectrum of the particles changed character in ways consistent with the transition from solar-dominated to interstellar-dominated plasma. The magnetic field direction shifted, consistent with the expected reorientation from the Sun's magnetic field direction to that of the interstellar medium. NASA confirmed Voyager 1's crossing of the heliopause in September 2013 after careful analysis of the plasma data. The announcement made headlines around the world. The first human spacecraft had entered interstellar space. The boundary crossed was not the edge of the solar system in the broad sense. The Oort cloud extends much further, and Voyager won't exit the Oort cloud's gravitational influence for perhaps 30,000 years. But it was a genuine boundary, a real physical transition from one environment to another, and the first time any human instrument had sampled the conditions of interstellar space directly. Voyager 2 crossed the heliopause in November 2018, entering interstellar space at a different location in the heliosphere from Voyager 1. And the two crossings provided the first comparative measurements of the heliopause boundary at two different points, revealing that the heliopause at Voyager 2's crossing location appeared somewhat different in character from Voyager 1's crossing. Colder, denser, with a slightly different magnetic field direction, providing information about the spatial structure of the heliospheric boundary that a single crossing could not have supplied. The ongoing measurements from both spacecraft in the interstellar medium are providing the first direct sampling of the material and fields in the immediate interstellar environment of our solar system. Information about the density, temperature, composition, and magnetic field of the local interstellar medium that no Earth-based or Sun-orbiting instrument could provide. The years after Neptune were scientifically quieter, but they were not empty. A flyby mission has an obvious drama when a planet fills the camera frame. The interstellar mission has a different rhythm. There are no close-up landscapes, no new moons appearing in images, no rings resolving into strands. Instead, the spacecraft measures invisible things: the solar wind, magnetic fields, energetic particles, plasma waves, cosmic rays, and the changing environment as the Sun's influence weakens. This kind of science is less visual, but it is not less real. The heliosphere is one of the largest structures associated with the Sun, and for most of human history, it was completely inaccessible. We could infer it from theory and from particles near Earth, but we could not go there. Voyager turned the outer heliosphere from a model into a measured environment. That change matters because the heliosphere protects the inner solar system from part of the galactic cosmic ray environment. It is not a solid shield, and it does not block everything, but it modifies what reaches planets, spacecraft, and life. Understanding its boundary helps us understand the Sun as a star moving through the galaxy, not simply as the light in our sky. In this phase, Voyager became less like a planetary camera and more like a weather station at the edge of the Sun's influence. It was no longer showing us worlds. It was showing us the environment around all worlds. These measurements are of genuine scientific value, filling in empirical detail about the environment through which the solar system moves as it orbits the galactic center. The heliopause is not a wall. It is a boundary between plasmas, pressures, particles, and magnetic fields. The solar wind does not simply stop at a hard surface. It slows, heats, piles up, and interacts with the surrounding interstellar medium. The interstellar medium is not still either. The Sun is moving through it as the solar system orbits the galaxy, creating a bubble that is shaped by motion, pressure, magnetic fields, solar activity, and the density of the local interstellar cloud. This is why the two Voyager crossings were so valuable. Voyager 1 and Voyager 2 crossed the heliopause in different directions, years apart, during different solar conditions. Their measurements showed that the boundary is not a simple sphere and not perfectly symmetric. The heliosphere breathes with the solar cycle. Pressure fronts from solar activity propagate outward. The local interstellar magnetic field shapes the boundary. Cosmic rays behave differently inside and outside the Sun's protective bubble. Inside the heliosphere, lower-energy galactic cosmic rays are partly deflected and modulated by the solar wind and solar magnetic field. Outside the heliopause, Voyager can measure them more directly, without the same degree of solar filtering. This makes Voyager's data important not only for heliophysics, but for cosmic ray physics. It gives a baseline for what the local interstellar particle environment looks like before the Sun modifies it. The spacecraft are therefore doing something no telescope can do. Telescopes observe light from a distance. Voyager samples the medium directly. It is not looking at interstellar space. It is inside it. The distinction between the heliopause and the edge of the solar system is subtle but important. The heliopause is a plasma boundary. It is where the solar wind stops dominating the surrounding medium. The Oort cloud, by contrast, is a gravitational structure, a vast, distant reservoir of icy bodies still bound to the Sun, extending thousands to tens of thousands of astronomical units outward. Voyager has crossed the first boundary, but is nowhere near the outer edge of the second. This means headlines about leaving the solar system can be both understandable and misleading. In one sense, Voyager 1 entered interstellar space in 2012 because it left the heliosphere. In another sense, it remains within the Sun's gravitational family and will take tens of thousands of years to pass through the region associated with the Oort cloud. The solar system does not have one edge. It has several, depending on what one means by edge: planetary orbits, Kuiper belt, heliopause, Oort cloud, gravitational dominance. Voyager teaches that boundaries in space are often conceptual as well as physical. The Sun's light reaches far. Its gravity reaches farther. Its wind reaches to the heliopause. Its cultural influence, carried by two small spacecraft, now reaches into interstellar space. Cosmic rays are one of the reasons the interstellar measurements matter. Near Earth, cosmic ray measurements are affected by the solar wind and the Sun's magnetic field. The heliosphere acts as a kind of filter, especially for lower energy particles. Scientists call this solar modulation. It means that a cosmic ray spectrum measured near Earth is not the untouched interstellar spectrum. It is the interstellar spectrum after passing through the Sun's protective bubble. Voyager 1 and Voyager 2, outside the heliopause, can measure particles beyond much of that filtering. This gives scientists a reference point for models of cosmic ray propagation through the galaxy. It helps connect local measurements near Earth with the broader astrophysical problem of how energetic particles are accelerated by supernova remnants, stellar winds, and other sources, and how they diffuse through galactic magnetic fields. The spacecraft are old, but the data still enters modern astrophysics. A measurement from a 1977 spacecraft can still constrain a 2020s model of the local interstellar medium. That continuity is one of the quiet pleasures of the mission. Voyager also gives future mission designers a benchmark. If humanity ever sends a dedicated interstellar probe, it will not be another Voyager in the simple sense. It will likely be faster, lighter, or more advanced, built with modern autonomy, modern communications, and instruments designed specifically for the heliosphere and interstellar medium. It may aim to reach hundreds or even 1,000 astronomical units within a human career, rather than taking half a century to reach the distances Voyager has reached. Concepts exist, but none has yet replaced Voyager's direct measurements. This gives the current spacecraft a unique role. They are imperfect interstellar probes because they were not originally built for that purpose. Their plasma instruments are limited. Their power is fading. Their trajectories are accidental from the perspective of modern heliophysics. And yet they are real. They are there. A perfect future mission on paper cannot substitute for an operating spacecraft already outside the heliopause. Science often works this way. The best available measurement may come from an instrument designed for another primary goal, extended beyond its original purpose by persistence and good fortune. Voyager's interstellar mission is exactly that, a planetary mission that lived long enough to become something else. The engineers and scientists who work on the Voyager interstellar mission face a set of constraints unlike those of any other spacecraft program in operation. The two spacecraft are so far from Earth that even the fastest radio signals, which travel at the speed of light, take more than 22 hours to travel from Earth to Voyager 1, and another 22 hours for any response to return. Real-time communication with the spacecraft is impossible. Every command must be planned and transmitted hours before it takes effect, and any anomaly or unexpected event must be diagnosed and responded to with information that is already more than 22 hours old by the time it arrives. The Deep Space Network, NASA's global network of large radio telescope antennas in California, Spain, and Australia, provides the communications link, allocating time to Voyager observations in competition with dozens of other active spacecraft throughout the solar system. The allocation of DSN time to the Voyager missions has required ongoing advocacy, as each antenna hour spent listening to the faint signals from the outer reaches of interplanetary space is an hour not available for the numerous other active missions competing for the same resource. Keeping Voyager alive has become a form of engineering archaeology. The spacecraft were designed by people using documents, assumptions, software languages, and hardware practices from the 1970s. Many original engineers are retired or gone. Some knowledge exists in manuals, diagrams, old test records, and institutional memory. When something fails, the team is not troubleshooting a modern spacecraft with modern diagnostics. They are often reconstructing how a system was intended to behave decades ago, under conditions no one expected it to face for this long. The 2023 and 2024 Voyager 1 data anomaly showed this clearly. The spacecraft was still receiving commands and transmitting a carrier signal, but the data were unreadable. Engineers traced the problem to a failed portion of memory in the flight data subsystem, the computer responsible for packaging science and engineering data. They could not replace the chip. They could not physically access the spacecraft. So they did something more delicate. They moved pieces of the affected code into other parts of memory and adjusted the software so the pieces would still function together. The repair had to be sent across more than 22 light hours of space. The team had to wait nearly 2 days to know whether the command had worked. In April 2024, engineering data returned. In June 2024, Voyager 1 was again returning science data from its instruments. It was not a dramatic cinematic rescue. It was slower and more impressive. Old code, moved around a failed chip, on a spacecraft built before many modern programmers were born. The 2025 thruster recovery was similar. Voyager 1's attitude control depends on tiny thruster pulses to keep its antenna pointed toward Earth. Propellant residue can build up in the narrow fuel tubes over decades, making thrusters less effective. Engineers had already switched between thruster sets over the mission's lifetime, but some thrusters had been considered unusable for years. In 2025, facing future communications constraints, the team succeeded in reviving long-dormant roll thrusters by rethinking the old failure and safely warming hardware that had been inactive for more than 2 decades. These stories matter because they show that Voyager's endurance is not passive. The spacecraft did not simply survive. It has been repeatedly saved by people willing to understand it in extreme detail. The time delay changes the psychology of command. If an engineer sends a command to a Mars rover, the delay is inconvenient but familiar, minutes. If an engineer sends a command to Voyager 1, the command becomes almost like a letter. It leaves Earth, crosses the orbits of planets, crosses the outer solar system, crosses the heliopause, and reaches a machine that will execute it long after the people who sent it have gone on with their day. Then the answer begins the same journey back. This makes even simple operations emotionally strange. Turning off an instrument is not a local switch. It is a command traveling for nearly a day to end a function that may have operated since 1977. Recovering data after an anomaly is not a phone call. It is a sequence of carefully tested instructions, sent into the dark, followed by waiting. The waiting is built into the mission. The further Voyager goes, the more the mission becomes a study in delayed trust. The Deep Space Network is the other half of Voyager. A spacecraft cannot be a mission unless someone can hear it. The DSN stations are spaced around Earth so that as the planet rotates, at least one complex can communicate with distant spacecraft. Goldstone in California, Madrid in Spain, and Canberra in Australia. The antennas are not simply receivers. They are part of a planetary-scale listening system, coordinated with mission schedules across the solar system. For Voyager, the DSN problem becomes extreme. The signal is faint because radio energy spreads out with distance. By the time Voyager's transmission reaches Earth, the received power is tiny beyond everyday intuition. The antennas must point precisely. The receivers must be cold and low noise. The signal processing must separate spacecraft data from background noise, interference, and the natural radio environment. This is one reason the mission feels almost like a conversation held across an ocean of time. Voyager speaks with a weak voice. Earth answers with enormous antennas. The spacecraft cannot shout louder. We have to listen better. The fact that the DSN can still communicate with both Voyagers is not a minor support detail. It is one of the mission's central achievements. The power situation grows more fragile every year. The radioisotope thermoelectric generators on both spacecraft produce power through the natural radioactive decay of plutonium-238, which has a half-life of 87.7 years. The heat output declines slowly, and the electrical output declines with it. NASA has often described the loss as roughly 4 watts per year across each spacecraft's usable power budget. At launch, each Voyager had hundreds of watts available. After almost half a century, every remaining watt has become a mission decision. This declining power budget has required regular choices about which instruments to turn off. This is not done casually. Every shutdown removes a kind of perception from the spacecraft. A camera loses the ability to see. A particle detector loses a population of charged particles. A plasma instrument loses a direct environmental measurement. But the alternative is worse. If the spacecraft falls below its power margin, fault protection can switch off systems unpredictably, and recovery at interstellar distances is slow and risky. By 2026, Voyager 1 had only two science instruments still operating: the magnetometer and the plasma wave subsystem. Its cosmic ray subsystem had already been shut down to save power, and on April 17, 2026, NASA shut down its low-energy charged particles instrument after nearly 49 years of operation. Voyager 2 had also lost several instruments. Its plasma science instrument was shut down in 2024, and its low-energy charged particles instrument in 2025. Its magnetometer and plasma wave subsystem continued to operate, and its cosmic ray subsystem was still listed as active while the mission team planned the next power-saving steps. The exact future sequence depends on power, temperature, communications, and spacecraft health, but the strategy is clear: preserve at least one useful science channel for as long as possible. This is why the last years of Voyager are scientifically and emotionally unusual. The spacecraft are not simply dying. They are being deliberately simplified. They are being reduced to the smallest set of systems that can still teach us something. The mission has become a careful act of subtraction. There is a quiet drama in that reduced data stream. A modern spacecraft near Mars can return images, spectra, engineering data, and software updates through networks designed for routine deep space operations. Voyager is different. Its signal is not only weak because of distance, it is precious because the spacecraft has so little power, so few active systems, and so little margin left. Each bit arrives after crossing a region no other working spacecraft has sampled. The number itself may be small, but the context makes it valuable. This gives the final mission a different kind of suspense from the planetary flybys. At Jupiter or Neptune, suspense came from discovery. What will the next image reveal? In interstellar space, suspense comes from continuity. Will the signal arrive? Will the instrument still be warm enough? Will the antenna remain pointed? Will the old code continue to run? Will the spacecraft survive one more power-saving decision? For a sleep documentary, that patience is part of the appeal. Voyager no longer rushes past planets. It listens to the dark and answers slowly. For a listener, the Voyager story works because it moves through several kinds of wonder. There is the mechanical wonder, that something built so long ago can still function. There is the planetary wonder, worlds we had never seen becoming real. There is the philosophical wonder, Earth reduced to a pale dot, and a golden record sent outward with no expectation of reply. There is the scientific wonder, direct sampling of interstellar space. And there is the human wonder, teams of people continuing to care about a machine that is older than many of the people now commanding it. A weaker version of the story would treat Voyager only as nostalgia. A stronger version treats it as a living mission. The spacecraft are historic, but they are not only historical. They are still part of present-tense science, present-tense engineering, and present-tense decision-making. That is rare. Most legendary missions are over. Voyager is legendary and not quite over. That tension is what makes the ending feel alive. For a sleep-focused science story, Voyager has a special rhythm. It begins with acceleration and fire, but it does not stay there. The launch is brief. The encounters are brief. The deeper story becomes quieter with distance. The spacecraft move from planets into darkness, from images into fields and particles, from discoveries visible to everyone into measurements that require patient interpretation. The mission itself becomes slower, fainter, and more minimal. That rhythm matches the subject. A spacecraft leaves noise behind. It leaves Earth, then the inner solar system. then the giant planets, then the familiar planetary map. It moves into a region where nothing dramatic appears to the eye, and yet something profound is being measured. The science becomes almost meditative. Density changes, magnetic field directions, plasma oscillations, cosmic ray counts, the slow decline of watts. This is why Voyager can be calming without becoming empty. It has enough story to hold attention and enough distance to quiet it. The 2026 shutdown of Voyager 1's low-energy charged particles instrument was especially painful because that instrument had been part of the spacecraft's interstellar identity. It had measured ions, electrons, and cosmic rays through the outer heliosphere and into the local interstellar environment. It helped scientists understand changes in particle populations as the spacecraft moved beyond the sun's wind. Turning it off did not mean the mission stopped being valuable, but it did narrow what Voyager 1 could still sense. The spacecraft kept the ability to measure magnetic fields and plasma waves, two of the most important remaining windows into interstellar space, but one more voice in the instrument suite went quiet. This is how the final science phase proceeds, not by losing everything at once, but by losing senses one at a time. The spacecraft becomes less capable, then simpler, then quieter. At some point, the last instrument will be switched off or fail. At some later point, the transmitter will no longer be maintainable. The mission team will listen, and nothing will come back. There is no need to romanticize that moment too much. It will be a technical end caused by power, temperature, aging components, and distance. But it will also mark the close of the longest continuously operating deep space mission in history. The decisions about which instruments to preserve longest have involved careful scientific argument about what each instrument measures and what questions its ongoing measurements can address. The plasma wave instruments and magnetometers have been prioritized because they continue to measure the properties of the interstellar environment, the scientifically novel region that neither spacecraft's builders could sample from Earth, and that no future mission is expected to reach for many years. There is also a practical human inheritance in the mission. Voyager taught generations of scientists how to plan encounters with worlds that no spacecraft had ever seen. It taught mission designers how to use gravity assists at planetary scale. It taught the Deep Space Network how to support communication across distances that had once been theoretical. It taught engineers what long-term spacecraft aging looks like when a mission survives decades beyond design expectations. It taught planetary scientists to expect surprise. That last lesson may be the most important. Io's volcanoes were not expected in the way they appeared. Europa's young icy surface opened a question that later became one of astrobiology's central themes. Uranus's magnetic field did not behave like a simple, tilted version of Earth's. Neptune's winds were stronger than the distant sunlight alone seemed to suggest. Triton was active at temperatures that should have made activity seem unlikely. Again and again, Voyager found that the outer solar system was not dead, simple, or finished. This changed the psychology of exploration. It made humility operational. When a spacecraft approaches a world for the first time, scientists can model, predict, and prepare, but they must leave room for the object to be stranger than expected. Voyager made that lesson unforgettable. The missions that followed Voyager can be read as responses to Voyager's questions. Galileo went to Jupiter and studied the system in orbit, confirming and deepening the case for Europa's ocean and directly sampling Jupiter's atmosphere with an entry probe. Cassini went to Saturn and spent 13 years studying rings, moons, magnetosphere, Titan, and Enceladus, turning Voyager's hints into entire fields of research. New Horizons flew past Pluto and then a Kuiper Belt object, extending the style of fast reconnaissance to worlds beyond Neptune. Juno studies Jupiter's interior, gravity field, magnetic field, and polar environment in ways Voyager could not. Europa Clipper and JUICE are built around the idea that icy moons may be ocean worlds worth detailed investigation. This is how exploration accumulates. A flyby sees enough to change priorities. An orbiter returns to stay. A lander or probe follows when the questions become specific enough. Voyager was often the first look, not the last word. Its greatest scientific gift may have been the creation of future missions. There is a human dimension to the Voyager mission that is distinct from its scientific and technical achievements. The people who built and launched Voyager in 1977 are now in their 70s, 80s, and 90s. Many of the scientists who planned the planetary encounters have died. The original science team members who saw the first close-up images of Jupiter's volcanic moon Io, who watched the Saturn ring system resolve into thousands of individual ringlets, who waded through the Uranus and Neptune encounters. These people gave significant portions of their professional lives to a project that began nearly half a century ago and is still technically ongoing. The Voyager mission has an unusual emotional resonance, even among people with no direct connection to it. Something about the image of two small machines, built with 1970s technology, still operating and still transmitting data after 47 years, now in interstellar space, carrying messages from Earth. Something about that touches a quality of human aspiration and persistence that transcends the specific scientific content of what has been measured. The engineer who worked on Voyager's trajectory calculations in 1974 and is now retired knows that the spacecraft whose path he computed is still moving along the trajectory he calculated, that the numbers he worked out are still accurate, that the physics he applied still governs the motion of an object billions of kilometers from where he is sitting. The biologist who helped select the images for the golden record knows that her choices are now in interstellar space, that the image of a woman nursing a child, or the sequence of DNA structure diagrams, or the picture of a sunset over the ocean is right now traveling through the material between the stars. There is a particular quality to knowing that a decision you made, an object you built, a message you composed, is currently farther from Earth than any human will travel in your lifetime or your children's lifetime, or perhaps ever. The Voyager mission endures not only in the spacecraft themselves, but in what they produced. Voyager was not the first spacecraft to head outward from the Sun. Pioneer 10 and Pioneer 11 came before it, crossing the asteroid belt and visiting Jupiter, with Pioneer 11 also visiting Saturn. They were pathfinders in the literal sense, proving that spacecraft could survive the radiation environment of Jupiter and navigate the outer solar system. They also carried plaques, simpler messages than the golden records, showing human figures, the spacecraft's origin, and a diagram of Earth's location. New Horizons came later, launched in 2006 toward Pluto and the Kuiper Belt. It was faster leaving Earth than the Voyagers, used a Jupiter gravity assist, and returned the first close-up images of Pluto in 2015, revealing another unexpectedly complex world. But New Horizons, despite its speed, did not duplicate the Grand Tour because the planetary alignment was gone. It was a different mission shaped by a different era. This context helps clarify Voyager's uniqueness. It was not the first outward spacecraft and not the last. Its uniqueness comes from the combination: two spacecraft, a rare planetary alignment for giant planets, a cultural message, and continuing interstellar science almost 50 years later. No other mission has combined all of those things. The scientific results, the discovery of Io's volcanoes, of Europa's ocean, of Neptune's enormous winds, of Triton's geysers, of Jupiter's and Saturn's and Uranus's ring systems in detail, are the foundation of a large fraction of what planetary scientists know about the outer solar system. The images, produced by instruments that are now antique by any technological standard, remain among the most scientifically important astronomical images ever made. And the golden record endures as a cultural artifact of a particular moment, 1977, when humanity first seriously considered what it would say to whoever or whatever might be listening, and decided to say, "Here is what we look like. Here is where we are. Here is the sound of the ocean and a Bach partita and a child laughing. Here is a brain in a state of love and wonder. Here is our attempt to be understood." There is something that feels important to say about scale here, because the full meaning of the Voyager mission depends on really holding the scale, not accepting it abstractly, but trying to feel it. 23 billion kilometers. That is how far Voyager 1 is from the Sun as of the early 2020s. The light from the Sun takes about 22 hours to reach it, 22 hours of travel at the fastest possible speed in the universe. Even at Voyager's speed of about 62,000 kilometers per hour, a journey of 23 billion kilometers would take, starting from Earth today, about 42 years to complete. And 23 billion kilometers is still entirely within the solar system's sphere of gravitational influence. The Oort cloud, the reservoir of comets surrounding the solar system on its outermost margins, extends to perhaps 15 to 50 trillion kilometers from the Sun. The nearest star, Proxima Centauri, is about 40 trillion kilometers away. Voyager 1, traveling at its current speed, would take approximately 70,000 years to reach Proxima Centauri if it were aimed at it. The universe is not naturally scaled for beings of our size, our speed, or our lifespan to travel between stars with ordinary propulsion. The distances are simply too large, and our capabilities simply too small. Voyager, the fastest thing humanity has ever made, the thing that has gone farthest, will take 70,000 years to reach the nearest star, and that star is one of 200 billion in our galaxy, and our galaxy is one of 2 trillion in the observable universe. And yet, within the solar system, that tiny, infinitesimal corner of one ordinary galaxy, 2 small machines launched 47 years ago have visited for planetary systems, discovered volcanoes on a moon of Jupiter, confirmed the ocean beneath Europa's ice, photographed the rings of Uranus and Neptune, witnessed the geysers of Triton, and sent back images and data that have shaped decades of scientific understanding. They are now in interstellar space, measuring the properties of the medium between the stars, transmitting their findings home at a rate that is usually closer to a few hundred bits per second than to anything a modern listener would recognize as an ordinary data stream. There will come a moment, probably within the current decade, when the last instrument on the last Voyager spacecraft falls silent for the last time. The power will not be enough to maintain it. The signal will stop. Earth will no longer receive transmissions from either spacecraft. At that point, both spacecraft will continue their journeys, silently, through interstellar space, carrying the golden records. They will pass through the galaxy at 17 and 15 kilometers per second respectively. They will drift far from the Sun, far from Earth, far from any planetary system, moving through the cold and relatively sparse material of the interstellar medium. They will continue, barring a collision, extremely unlikely in the vast emptiness of interstellar space, for billions of years. Eventually, the Sun will become a red giant, expand to perhaps the orbit of Earth, and then shed its outer layers as a planetary nebula. Earth, if it survives at all, will be a stripped, sterile rock. The Voyager spacecraft will be somewhere in the outer regions of the galaxy, still drifting, still carrying their golden records in the interstellar dark. The silence, when it comes, will not mean the Voyagers have stopped. It will mean they have stopped speaking to us. The spacecraft themselves will keep moving. Their trajectories are not powered. Their motion is orbital and interstellar, governed by gravity and inertia. They will coast through the galaxy long after their transmitters fail, long after their power systems can no longer support electronics, long after the last command from Earth has been sent. Their next stellar encounters are not true arrivals. Voyager 1 will pass within about 1.6 light-years of Gliese 445 in roughly 40,000 years. Voyager 2 will pass within a few light-years of several stars on timescales of tens to hundreds of thousands of years. These are close only by interstellar standards. They will not enter those systems. They will not slow down. They will not be captured. They will drift past, silent and dark. The physical survival of the spacecraft is also a strange thought. The electronics will fail. The power will fade. The transmitters will go silent. But the structures themselves, the booms, the antenna, the record cover, the record, the bus, the remnants of the instruments, will remain as objects. Interstellar space is not perfectly safe, but it is sparse. Micrometeoroid impacts are possible over enormous timescales, and radiation will slowly alter materials. But there is no atmosphere to corrode the spacecraft, no weather to erode them, no surface to bury them. They will become artifacts without observers. Human-made things no human can reach. Archaeology usually looks backward on Earth, digging through soil, stone, cities, bones, and pottery. Voyager creates a different kind of archaeology, not buried in the past, but drifting into the future. The golden records may outlast every building standing today. They may outlast languages, nations, archives, and digital formats. That does not guarantee that anyone will find or understand them. Survival is not communication, but survival still means something. 2 physical records of Earth will move through the galaxy long after the world that made them has changed beyond recognition. This is not a reason to exaggerate their importance. The galaxy will not notice, but meaning does not require the galaxy to notice. It is enough that the act was made and that the objects continue. This is another scale that Voyager teaches. Reaching interstellar space is not the same as reaching the stars. The heliopause is far by human standards, but near by stellar standards. Voyager 1 has crossed the Sun's plasma boundary, but the nearest stars are still thousands of times farther away than the spacecraft has traveled. Interstellar space begins long before interstellar destinations become reachable. One last detail makes the mission feel even stranger. Voyager is both extraordinarily far away and still close to home. 25 billion kilometers is almost impossible to imagine. It is far beyond Neptune, far beyond the planets, far enough that light needs almost a full day to make the trip. And yet compared with the nearest star, it is still a beginning. The distance from the Sun to Proxima Centauri is measured in light years, not light hours. Voyager has crossed a real boundary, but it has not crossed the great distance between stars. It has entered the shoreline of interstellar space, not the ocean's far side. This does not diminish the achievement. It clarifies it. The first step into a larger domain is still a first step. A shoreline is still a boundary. Voyager is the first human-made thing to carry functioning instruments across the Sun's wind boundary and report back from the other side. That is enough. There is a lesson in that modesty. Exploration does not require pretending we have conquered the universe. It is enough to measure a little farther than before, to see one more world clearly, to cross one more boundary, to keep a signal alive one more year. Voyager's greatness is not that it made the stars reachable. It is that it made the edge of the Sun's bubble real. The rest remains waiting. It is also a reminder that exploration has different speeds. Some discoveries happen in a flash, when an image appears and a new world is suddenly visible. Others happen slowly, through measurements accumulated year after year until a boundary, a pattern, or a change becomes unmistakable. Voyager has done both. It gave humanity moments of sudden revelation at the planets, and then decades of slow revelation at the edge of the Sun's influence. That combination is rare. A mission can be spectacular, or it can be patient. Voyager managed to be both. That distinction makes the achievement smaller and larger at the same time. Smaller, because Voyager is not a starship in the science fiction sense. Larger, because the first step beyond the heliosphere was accomplished with 1970s technology, careful navigation, radio dishes on Earth, and a willingness to keep listening for half a century. In 10 billion years, after the sun has become a white dwarf and begun cooling toward eventual darkness, both Voyager spacecraft will still exist, still carrying their records, still moving through interstellar space. The universe will be older than it is now by a factor of almost 2, and what it will contain and what will happen in it is impossible to predict. But two small machines, built in the 1970s by a species on a small planet in a spiral galaxy, will still be drifting through whatever the universe has become, carrying messages from a civilization that no longer exists in the form it had when it built them. The Voyager mission is not yet over. The transmissions are still coming for a few more years. The measurements are still being made. The data is still being analyzed. The instruments are still running, some of them on power generated by the decay of plutonium atoms that have been emitting heat since 1977. It is, by any measure, an extraordinary thing that human beings have done. Not the most scientifically sophisticated thing, not the most powerful thing, not the most expensive thing, not the thing that solved the hardest problems or created the most useful technology. Just two small machines, sent into the dark, measuring things and reporting back, carrying a careful and hopeful record of what Earth was, drifting now through the first miles of a journey that will last longer than the solar system. That seems like a good thing to take into sleep. The universe is unimaginably large, and human beings are very small, and somewhere in the dark between the stars, moving at 17 kilometers per second and still transmitting, is evidence that small things can make long journeys. There is a quiet paradox in Voyager. It is one of humanity's greatest technological achievements, and at the same time, it is almost fragile beyond belief. A tiny transmitter, a fading power supply, hydrazine thrusters with residue in their fuel lines, software written for memory measured in kilobytes, a tape recorder from another technological era, a dish antenna that must stay pointed at one moving planet across billions of kilometers, a signal so faint that it can disappear into noise if Earth stops listening carefully enough. And yet that fragile system has outlived empires of technology on Earth. It has outlasted the machines that built it, the computers that controlled its launch, and many of the people who designed it. It has traveled through the outer planets, the heliosheath, the heliopause, and into the local interstellar medium. It has turned fragility into duration. The two spacecraft are also different characters now. Voyager 1 is the faster and farther one, climbing above the plane of the planets, the first through the heliopause, the record holder for distance. Voyager 2 is the fuller planetary traveler, the only spacecraft to have visited all 4 giant planets, descending below the ecliptic after Neptune. One became the farthest messenger. The other became the complete grand tourist. Together they divide the mission's meaning, distance and breadth, endurance and encounter, interstellar science and planetary discovery. That symmetry helps the story feel complete. Voyager 1 looked back and made the pale blue dot. Voyager 2 went on and gave humanity Uranus, Neptune, and Triton. Voyager 1 crossed into interstellar space first. Voyager 2 crossed later, giving comparison. They are twins, but not duplicates. Each carried the same record from Earth. Each took a different path into the dark. For a viewer or listener, that matters. The mission is not one machine doing one thing. It is a paired story, with 2 trajectories and 1 origin. It is endurance made measurable, a tiny voice, kept alive by patience, still crossing the dark between worlds. It also leaves behind a useful feeling. Exploration does not always look like speed or noise. Sometimes it looks like care repeated for decades, a fragile signal protected by people who know exactly how much can be lost if one command is wrong. Voyager's distance is impressive, but its continuity is what makes it moving. That is the emotional core of the mission. Voyager is not powerful in the way a rocket launch is powerful. It is powerful in the way a candle is powerful when it is still burning in a very large darkness. And that makes it a fitting story for sleep. Not because it is small, but because it is patient. Not because it is quiet, but because its signal has crossed more silence than any human signal before it. Not because it is finished, but because it is still, for a little while longer, speaking. Good night.